This video is on the objective calculate the test statistic, or the t-value, a t-score, for a two-mean hypothesis test for population variances or standard, if remember, variances are just the standard deviations squared. So you could say for population variances or population standard deviations assumed to be equal. And if the population variances or standard deviations are assumed to be equal, then we're going to be calculating what's called a pooled estimate of the standard deviation of the sampling distribution for the difference in sample means, and I'll get into all that means in a second. Alright, so before I actually get to the question from your homework, I want to show you, remember this is, when there was another objective where we calculated a test statistic, but in that particular case the population standard deviations were unequal, right? Assumed to be unequal. You have what's called a non-pooled estimate of the standard deviation for the distribution of sample differences, difference in sample means. This was that non-pooled estimate right here. Right. Well, what resulted when we did no pooling, right? And hopefully this all rings a bell, when I talked about when we had two populations with unknown standard deviations and assumed the population standard deviations or population variances were unequal, the non-pooled scenario. So what I'm going to do now is talk about the other scenario that could come up when you're doing a test of two population means when the population standard deviations are unknown. All right, so this is part two, I guess we could say. All right, and this is where, again, you have unknown sigmas, but this time you're assuming that they're equal. So this is assuming that the population standard deviations or the population variances, because again the variances are just standard deviations squared, assume they're equal. Alright, so in this particular case, this is what's called a pooled scenario. Alright, where we're going to be calculating a pooled estimate of the standard deviation for the difference in our two sample means, and you'll see what I mean in a second. I'll draw some pictures. So again, a picture similar to that first one. So you have two separate populations, right? Two independent populations. Population 1, and it's got a mean, say called mu1, and it's got a standard deviation sigma 1, but this is again unknown. Unknown. Alright. And I have a second population, a separate population, population 2, and again its mean is called mu2, mu sub 2, and its standard deviation sigma is again unknown. I don't know what either of these are, and that's usually the case. Right? You usually, if you don't know the population mean and you're trying to test about it, estimate it, you more than likely don't know the population standard deviation as well. But this time, right, as opposed to the last scenario, we're assuming that sigma 1 is equal to sigma 2. Right? Assume they have the same standard deviation or the same variance. Right? Sigma 1 squared equals sigma 2 squared, same thing. Alright, well, just like the non-pooled, just like the non-pooled scenario, right, we're going to be taking samples from these populations. So I'll take a sample of objects, people from population 1. It'll have a size of n1. That's the size of the sample. Have a mean of x1 bar. And a standard deviation of s1. I'll just say SD for standard deviation. And the same thing from population 2. From the other population, I pull a sample. And it's going to have a size of N2, a mean of X2 bar, and a standard deviation of S2. All right. Now, if you recall from the central limit theorem, if the sample sizes were big enough, or if the populations were approximately normal, then the distributions of these means, say from population 1, look at them separately. The distribution of these x1 bars would be a student's t distribution, right? That's because sigma was unknown, sigma 1 was unknown, with n1 minus 1 degrees of freedom. And the mean of these sample means, the mean of these x1 bars for samples of size n1 would be the mean of the population mu1. All right. And the standard deviation of these x1 bars would be the standard deviation of the population divided by the square root of the sample size. All right. Now here's where things get a little tricky. When these population standard deviations are assumed equal, instead of using our sample standard deviations S1 and S2 as estimates of sigma 1 and sigma 2, we're going to do what's called pooling them and creating a pooled standard deviation for the two samples. So before I write down what this is, we need to calculate a pooled estimate of the standard deviation. I'll say of SD, right? And this is going to be labeled S sub P for pooled, S with a subscript of P for pooled. All right, and the way this is calculated, again, it's as if you were putting these together, these samples together, but still considering them as separate, but you're thinking about them as one. And it'd be the square root. Make a big square root. And then remember, in the numerator for standard deviation calculations for samples was the sum of all the squares of the deviations. How far away they were from every value was from the mean, and then squared. Well, I only have these values S1 and S2. If we take S1 and square it, that gives us the variance. And I multiply this by the sample size minus 1, if I multiply this by n1 minus 1, this right here, n1 minus 1 times, the variance 1, s1 squared, this gives me the sum of the squares of the deviations for all the values in sample 1, without knowing any of the values in sample 1. And I do the same thing, plus, same thing for sample 2. Take the sample size minus 1 times S2 squared times the variance for sample 2. And this will give me the sum of the squares of the deviations for all the values in sample 2 without knowing the values in sample 2. All right, and then this gets divided by basically the degrees of freedom for each of these t distributions put together. n1 minus 1 plus n2 minus 1. So the denominator here is n1 plus n2 minus 2. Alright, so this looks funky. Looks pretty big. But this, again, when you're assuming the population variances, population standard deviations are equal, instead of using S1 and S2 in our estimates of sigma 1 and sigma 2, we're we're going to be using this pooled standard deviation, SP. So an extra calculation to make, unfortunately. So back to this again, the mean of the means for x1, the mean of the x1 bars would be mu1. The standard deviation of the x1 bars would be, usually it's sigma 1 divided by the square root of n1, but I don't know sigma 1, so we're going to use this S pooled divided by the square root of n1. And then very similar over here, right? If you look at this second population, the distribution of these x2 bars for samples of size n2 would be a student's t distribution with n2 minus 1 degrees of freedom, right? And the mean of these x2 bars would be mu2. The standard deviation of these x2 bars, again, would not be, normally it would be sigma 2 divided by the square root of n2, but again, we're going to estimate sigma 2 with SP, right, divided by the square root of n2. And again, the only reason I'm doing this is because we're assuming the population things are equal, so that's why we can use this pooled standard deviation to estimate both. All right. And then from here we look at, all right, what's the difference between these sample means? And you saw this in the first scenario as well, the non-pooled scenario. Now we're going to look at the distribution of x1 bars minus x2 bars. And in this pooled scenario, the distribution of all the x1 bars minus x2 bars will be a student's t distribution with then, for the non-pooled scenario, the number of degrees of freedom was the smaller of n1 minus 1 and n2 minus 1. For the pooled scenario, this pooled scenario, the number of degrees of freedom for the distribution of x1 bar minus x2 bar will be this denominator here, basically the sum of the degrees of freedom. Again, we're kind of putting these together, we're pooling them. n1 minus 1 plus n2 minus 1 would be n1 plus n2 minus 2 degrees of freedom. Okay, and we'll keep that in mind for a later video. I'll bring this page back up. There's another objective where you're just finding the degrees of freedom for a test about two population means in either the non-pooled or the pooled scenarios. And then the mean of these, x1 bars minus x2 bars would just be the mean of x1 bar, mu1, minus the mean of x2 bar is mu2. And the standard deviation of x1 bar minus x2 bar, and I mentioned this in the non-pooled scenario. Forget standard deviation for now. If we look at variance, the variance of the difference between two variables that are independent, right, we're assuming that these populations are independent, would be just the sum of their individual variances, right? So it'd be s, square this, and add them up. So I'd have sp squared over n1 plus, and then sp squared over n2, but that was the variance of the difference of two independent variables. We're looking at the standard deviation, so I just take the square root of that. Right. Now, something you may notice is that both these terms now have this pooled standard deviation squared in common. So I could factor that out, and then the square root of sp squared would just be sp. So you can have sp on the outside, and if I factor that out, then I'll have 1 over n1 plus 1 over n2 inside. So you might be seeing this instead as the standard deviation for the difference in sample means, x1 and x2 bar. All right. And finally, after all this, the test statistic for our sample means. So in this scenario, again, this pooled scenario, where you're assuming population variances are equal, the test statistic, and we're dealing with students' t-distribution here, is a t-score. And it's, what's the difference between our sample means? So x1 bar minus x2 bar minus what's the mean value of this t-distribution for the difference in sample means? It's this mu1 minus mu2. And then we're finding a t-score, right? We take our sample mean differences minus, what's the value in the middle, which will usually be 0, because this is going to come from the null hypothesis, in which we're most likely going to be assuming that mu1 and mu2 are equal. So this is going to be 0 here. So really the numerator you can just say is x1 bar minus x2 bar. And then we're going to say how many standard deviations is that? We're going to divide by the standard deviation of this difference of means, which is this pooled standard deviation SP times the square root of 1 over n1 plus 1 over n2. Right. So again, this is a test statistic based on this distribution here, right? We're focusing on the distribution of what happens when I take the difference in sample means, right? And here's our test statistic. And then if we're doing the critical value approach, right, I would compare this to certain critical values for whatever the t-distribution is with so many degrees of freedom. If we're doing the p-value approach, I'd find the p-value for our test statistic in that particular t-distribution. But we're not going any further than this just yet. Okay, so that was a lot again, right? The non-pooled versus the pooled scenarios. But you have to pay attention to which is which. So if you look at the question here, now again, if you'd like to see more about this or what they have to say, click on more instruction, and look at their videos, their notes, their examples, and hopefully they help. Alright, where it says here, we are doing a two-mean pooled t-test. They even tell us right from the beginning. Alright. We have two samples with sizes, n1 equals 21, n2 equals 19. The population standard deviations are unknown, right? That's why we're using a t-score here, students' t-distribution, but assumed to be equal. That's what makes it pooled. That's what makes this test going to be a pooled t-test, because the population standard deviations are assumed to be equal. So we find the sample standard deviations and use them to calculate a pooled standard deviation SP. Right. So for sample 1, the sample standard deviation for sample 1 is 13.3, and the mean of sample 1, right, x1 bar, is 50. Sample 2, second standard deviation is 13.8, and the second sample mean is 40. So what are the test statistic and the degrees of freedom to perform this test? All right. So again, I've mentioned this here, back on my paper. The test statistic is this crazy thing here, and like I said, in most cases, and definitely in this one, this mu1 minus mu2 here is going to be the number 0, so there's really no need to write it. You're going to be assuming that that's 0 from the null hypothesis in almost every case you come across. And the number of degrees of freedom of our t-distribution in the pooled scenario is n1 plus n2 minus 2. All right. So here, let me write this information we're given down. All right. So for this particular problem, sample 1, we're given this the sample size 1 is 21. The sample mean for sample 1 is 50, and the standard deviation for sample 1 is 13.3. And then for sample 2, the sample size is 19, The second sample mean is 13.8, and the second sample standard deviation, oh, I'm sorry, that's 13.8. The second sample mean was 40, my bad. And the second sample standard deviation was 13.8. Now again, we are in the pooled scenario, right, where again the population, you're assuming here that sigma 1 is equal to sigma 2, right? The population standard deviations are assumed equal in this scenario. So I need to find this SP in order to be able to calculate my test statistic later. Okay, so remember this is the square root, big square root, and I'll pull up a calculator of, n1 minus 1, so 20, times s1 squared, so times 13.3 squared, plus then n2 minus 1, 18, times s2 squared, so 13.8 squared. Then all of this divided by the n1 minus 1 plus n2 minus 1. So 20 plus 18, 38. And this is also going to be the number of degrees of freedom, the n1 minus 1 plus n2 minus 1, or n1 plus n2 minus 2. This is going to be the number of degrees of freedom for our t-distribution as well, 38 degrees of freedom. Alright, now let me punch this in. So I'll pull up a calculator. So again, square root, and then in parentheses in this numerator we have 20 times 13.3 squared, and then plus, and then 18 times 13.8 squared, and close parentheses. That's all in the numerator, divided by, and then again make sure this is all underneath your square root symbol, and then divided by 38. Alright, so this pooled estimate of the standard deviation is approximately 13.54. Right. Now, I'm just going to leave this number the way it is here, because I'm going to be I'll just use this full number in my next calculation of the test statistic. Right, so the test statistic for our samples, our two sample means, is this t-score. Remember, it's going to be the difference in the sample means, x1 bar, 50, minus x2 bar. Alright, that's going to be in the numerator. So just 10 in the numerator. Divided by SP, right, so this 13.54 number, times the square root of 1 over n1, so 1 over 21, plus 1 over n2, this is 1 over 19. Again, that's all in the square root. And let me round this to 2 decimal places after. So on the calculator, my numerator is 10, right? 50 minus 40, divided by, and then since there are two factors, two things being multiplied down here, I'm going to put the denominator in parentheses. So I set a parentheses here, and then the SP is my previous answer. So I'm just going to go second, and then above the negative number, a negative sign is the answer. That's the previous number, times the square root, and then all inside this square root is 1 over 21 plus 1 over 19. And make sure that 1 over 21 plus 1 over 19 is all inside the square root. And then I close the parentheses. That's finishing the denominator off. And we're getting approximately 2.33. Right. So, our sample means, the difference between those sample means, right, 50 minus 40, that difference is 2.33 standard deviations above 0. Is 2.3 standard deviations above the assumed mean from the null hypothesis, the assumed difference of means, which is, reasonably far away. Now, depending on the significance level, we'll see whether or not we would reject the null hypothesis, but we at least have the test statistic, right, a t-score here. And like I said earlier, also the distribution of these difference in sample means, right, x1 bar minus x2 bars, would be a student's t-distribution with 38 degrees of freedom. That was the n1 plus n2 minus 2. And so we're answering this, the 38 degrees of freedom, and we're answering this for our test statistic. Let's go back. Now it's a multiple choice one. So look, I mean, every single one of them has SP equals 13.539. So they found SP for us, it looks like. But we found it also as 13.539 in the calculator. And yeah, then make sure the calculation for the t-score is the same I wrote up earlier, right? 50 minus 40 divided by, and then SP times the square root of 1 over 21 plus 1 over 19 is 2.33. But the degrees of freedom is wrong for this choice, right? It should be 38 degrees of freedom. So we're looking at this option down here. The degrees of freedom for the t-distribution is 38, and the calculation of 2.33 for our test statistic is correct. Okay, wonderful. So again, you got to pay close attention. Hopefully, this one they told you, they said it's a pooled test. They told you. But you got to pay attention. In future problems and other problems, you may have to see that yourself. So again, if they ever say anything about the population standard deviations being assumed equal, or the population variances are assumed equal, then you're going to have to calculate this SP, right, this pooled estimate of the standard deviation, and then find your test statistic from there. Alright, so hopefully watching this video, and I mean it's a long one, but hopefully watching me do this and reading the answer explanations here and looking at the more instruction, hopefully all that stuff helps you when you go about doing this on your own. And thank you for watching.